Okay, great. So I'm going to give a brief introduction. This is a talk that Haresh Fatahi gave at the EarthScope 2023 short course. So I'm going to summarize, shorten it because I'm only going to cover SBAS. You should check the recording available from EarthScope from the last August short course to get the full story from Haresh. Haresh has been working with a lot of people. I'm going to only cover the SBAS part of this. That's I'm going and skip some of the I've deleted some of the other part. It's about PS. So we covered this. Josh covered this yesterday about how InSAR works. I'm not going to go into this in any detail. We're looking at the phase change of the interferogram, which is the difference between the phase at time 1 and time 2. This is actually an interferogram from the BAM earthquake that I worked on, well, 20 years ago. It was 2003 earthquake. So the key thing about InSAR analysis is that the phase that we measure, this difference in phase between the two dates, is a combination of a number of effects. There is the displacement here. That's what we really want to measure. But there's also effects of the atmosphere, which includes both the ionosphere and the troposphere that the radar waves go through. There's some phase that's due to the geometry. If these two satellite locations are not exactly the same, there's a geometric phase that's combined with topography. Normally we can calculate that and remove it. There's changes in the surface scattering. That's if the surface changes between the two dates. And then there's noise, which is other effects that in the hardware and software used to make the interferogram. So the key thing is that these components, the displacement that we want to measure is on the order, in most cases, of millimeters to centimeters. Sometimes for earthquakes or volcanic eruptions, there's tens of centimeters or even meters of displacement, in which case then we don't really need time series analysis. But in a lot of cases, we're looking at moderate to small motions, and so that are millimeters to centimeters. The atmospheric effects can be a few centimeters to tens of centimeters or even meters, especially with the ionosphere at L band. And that's a key part that we have to work on with time series analysis. The geometry is generally only a few centimeters, as long as the distance between the satellite locations is low. That's true for Sentinel-1, ALOS-2, and it will be true for NISAR. So that used to be a big problem, but it's less of a problem these days. The changes in scattering properties in the targets is another thing that's usually on the millimeter level, but it can be an additional effect. And then there's the noise, which can cause a loss of coherence, or what usually called decorrelation. So especially when we're using short radar wavelengths. On the left here is a X-band interferogram. This is the 3 centimeter wavelength. And if you use a very long time interval with X-band data, it's completely decorrelated. There's no coherence in the interferometric phase, so we can't really measure any deformation. But by doing time series analysis of all the dates in between over that 2.5 years in San Francisco, Haresh was able to make this effective interferogram. It's not from directly from the original data, but it's by adding up the interferograms in between using the time series analysis. You're actually able to get a map of the surface formation. So that's one of the key reasons people do time series analysis. It's not so important at L-band because the L-band doesn't decorrelate nearly as quickly. That's the main reason why we're launching NISAR. Another reason is to avoid the noise from the atmosphere. In this case, the interferogram here in the middle is showing an honest interferogram that's heavily contaminated by ionospheric effects over the Galapagos Islands. And by doing time series analysis, we're able to, in most cases, reduce or sometimes eliminate the effects of the atmosphere and get out the actual surface deformation that's shown over here. So the other reason to do time series analysis is to actually understand how the ground is moving with time. This is an example of a time series for an area with an earthquake in it. You can see there was before the earthquake, there was some kind of linear trend of motion, possibly due to a fault slip deep in the earth, the interseismic loading. There's a sudden offset at the time of the earthquake, and then there's a post-seismic deformation that's continuing to move after the earthquake. And by doing time series analysis, we can actually get this time history. Volcanic eruptions have similar types of time history where there's oftentimes a buildup of magma, sudden drop as the magma is erupted, but then post eruption motion. So these are the kind of things that we want to look at. And then for groundwater, one of the other examples that I'm going to actually show later, there's often a seasonal cycle because the groundwater levels go up and down every year due to when it rains, when it's dry. So for time series analysis, people often divide the time series analysis into two different types. There's the so-called distributed scatterers. That's where there's a bunch of smaller reflectors within each pixel that add up to form a distributed set of radar scatterers. And then there's the case where there's one very bright reflecting object within a pixel, and that's what people call a permanent scatterer that dominates. And that is a different type of analysis that I'm not going to talk about today because it's not part of SBAS, and it's not something that I'm very familiar with. I've always worked with this distributed scatterer analysis. So PS and DS is one of the terms that people often use for time series analysis. And I'm only going to be talking about the DS or distributed scatterers and SBAS analysis today. see Haresh's talk from last August for the whole story on PS. So for distributed scatter time series analysis, we have a set of interferograms. We do a network analysis, and then we estimate what's the for all the pixels. And then you end up with a set of displacements for each date that was in your data set. And those measurements are always relative to a reference point that's somewhere in the image and a reference date. So we have to define both of those in time series analysis. In most cases, people have used a whole network of interferograms. NISAR is the NISAR project is only going to be processing adjacent in time interferograms. So it won't have a whole network available. You would have to do your own analysis to add all these extra connections, but you're able to do time series analysis as long as every dot is connected. And if you have the adjacent in time interferograms, it's possible to do time series analysis. As Haresh gave this talk last August, he talked about the standard SBAS analysis that's been around for 20 years and some newer full covariance-based algorithms that require this more connected network, and I'm not going to be talking about today. So the key things is to make a stack of co-registered SLC images, make a set of interferograms, do the phase unwrapping of each interferogram, then to create a network of small baseline unwrapped interferograms. For the case of NISAR, these are called gun Ws, and we have the ARIA Sentinel-1 gun W files that are made from Sentinel-1 data and in a NISAR-like format, and NISAR will have their gun W files. Then you take that set of unwrapped interferograms and do the time series inversion, and it extracts does a least squares inversion to estimate what's the actual displacement on each date. And then the people often do some post-processing to make time series. There's some optional corrections that I'll talk a little bit about, including tropospheric delay and DEM errors. So it's actually done by doing this matrix inversion. The A matrix here tells which dates are used for each interferogram. The set of interferograms is what you put in as the known on this side of the equation, and this unwrapped phase time series relative to your reference point and reference time is the unknown. So you can see this is a standard linear equation, and we have to do a network, a matrix inversion to get the inverse of A to estimate what the phi is from the delta phi. So there's also a calculation that's done in MintPy and other time series analysis. That's the deviations of the fit from the from the different interferograms, and that gives an estimate of what's the temporal coherence and how consistent the different interferograms are from your network. So that's a key uh, error analysis method. So this is just an example. This is actually from work that Haresh did using both PS, where we are extracting just the pixels that have the strong scatterers, um, and the distributed scatterers from SBAS. They've done work on how to combine those two together. Um, that's something that we're not covering today, but this is just an example of how what your time series can be used for at the end is to do an estimate of what's the linear velocity of the ground surface. Um, and in this particular case, if you look at these points C and D labeled here, the time series shows that it was relatively stable for some amount of time, and then there was a sudden creep event, and this fault here, called the Concord Fault in Northern California, suddenly moved by several centimeters. Well, a little over around a centimeter. Um, and that's one of the types of analysis we can get from looking at the uh, time series. There's also at points A and B, there's an area where there's a strong subsidence signal, and E and F here shows that there was also a seasonal component where every year the values were going up and down, and that is another type of signal that we can estimate from the time series once it's calculated. This is another example that Harash made from uh, doing a stack of SLCs that were processed with the full covariance algorithm. And in this case, this was a large earthquake that happened in Kurdistan, western part of Iran. In 2017, and you can see that in this particular area, the land was relatively stable before the earthquake. There was a large displacement during the earthquake, and then there's a post-seismic displacement afterwards. So error analysis is a key part of time series analysis. We're only talking about the DS part of the analysis here, but there's the other PS and the combined PS-DS analysis. Those, depending on which type of analysis you're doing, you can get different types of measurement of estimates. But the final result is basically the same in from all these methods, that you get this time series of what's the unwrapped phase or estimated surface displacement at each date in the time series relative to the reference point and reference date. So this is an example. In some cases, there's a problem with co-registration of the interferograms. This is especially a problem with L-band data. This was a L-band data set that we used in the InSAR course from ALOS, the Japanese ALOS satellite, ALOS-1 satellite. And if you just use the orbits, the two images are not aligned completely accurately, and ends up with a very low coherence interferogram. But after doing a matching to adjust this co-registration, then the interferogram is much clearer. That's in this case almost entirely due to the ionosphere, and NISAR data will be processed with an estimate of what this azimuth, what this misregistration is from the other ionospheric data, so that we are hoping that the ionospheric misregistration will be largely removed from the ARIA GunW files. Phase unwrapping errors are a big problem in a lot of cases. This is a big topic. I'm not going to get into this in any detail, but that's something to be worried about. In some cases, if you see your time series has a sudden jump between different patches in the interferogram, that's a very likely to be an error in a phase unwrapping. The geometry is something that used to be a problem for data sets where the baselines were long. This is less of a problem with NISAR. So in most cases with Sentinel-1 data and what we expect for NISAR, the DEM, the long baselines are not going to be present. That means that the errors due to the DEM not being completely correct are also less. And MintPy has an option to estimate what this geometric error is, but I've used that. I've kept that turned off for processing Sentinel-1 data, and but that is an option. So then there's the ionosphere. I mean the atmosphere. This is an example from one of Haresh's older papers showing data from the ENVISAT satellite. In the ENVISAT satellite, they actually had both the radar and an optical instrument called MIRIS that included infrared wavelengths that actually measured the water vapor in the atmosphere. And during the day, it was possible to use the MIRIS data acquired. If it's during the day and cloud-free, then you could extract an estimate of what the water vapor effect on the radar propagation was, and then subtract that from the interferogram to get a corrected interferogram from the MIRIS instrument. But NISAR will not have this kind of extra instrument on board, and Sentinel-1 does not have that instrument. Only NVSAT had that instrument operating, which was because it was a much larger satellite. The other way to estimate the tropospheric delay is just by doing a lot of interferograms and then doing a fit. And after doing the time series analysis, you can usually reduce the tropospheric delay quite dramatically by just doing the mini interferograms. The ionospheric delay is a big deal for L-band, and this is going to be, that's why NISAR has been designed with these two bands, because the ionosphere actually has a different amount of delay depending on the radar wavelength. By having two different wavelengths measured by the NISAR instrument, then we can take make interferograms from those two wavelengths and do some calculations on that on the difference between those two interferograms to estimate what the ionospheric delay is, or what the relative ionospheric delay is, and subtract it. So that's going to be provided as a NISAR correction layer in the NISAR GunW files. This was a test that they did with the impact of ionosphere on the Sentinel-1 data. No, this was I'm not sure exactly what Haresh was showing in this one. No, he did do ionospheric corrections on the L-band data of ALOS for an earthquake that happened in 2007. That's what this is about, the Tocopilla earthquake. The other thing that's become much more widely followed in the recent years is the fact that when you have multiple interferograms for the same dates, you can take what they call phase triplets. This is taking 3 different dates with the pair between I and J, the pair between J and K, and the pair between K and I. And this phase should be 0 if the interferograms are consistent. If there's no multi-looking in the data, then that will be 0 by definition. But for interferograms that have been multi-looked, like all the GunW files that we are looking at, then this in practice will not be equal to 0. And this can cause, this was some recent papers have showed that this can actually cause a bias in your velocity estimate if you're only using short-term interferograms. But so that's this was something that was published last year or 2 years ago now by Yuji Zheng, and how this phase closure bias can actually accumulate with time and cause an apparent displacement. And this was a dry lake bed in California. So here are the references. The Yuji Zheng, Fatahi, and Rosen was on the phase closure bias. That's a recent paper. Ansari and these Ansari papers are also similar about the phase bias. So those are good things to look at if you want to get into that type of detail. And these are the links to ICE2, ICE3, MidPy. Fringe is the framework that does the PS and DS analysis, and another new more PS analysis package is called Miami phase linking pi. MyApple. I don't think that's really pronounceable. It's not like MidPy. Okay, so that's a brief introduction. I didn't want to go into too much detail, but give you an idea of what's involved with SBAS analysis before we actually do it.
Thanks, Eric. And before you jump into your demo, we do have a few questions in the QA.
Okay.
Maybe I'll just read them just so that they're documented on the recording as well.
Okay.
So Tanya Mayorga Torres asks, please, Eric, maybe are there literature about dominant scatterer for InSAR applications with mass movements, since the type of soil is an important factor to consider?
Are the dominant scatterer? Yes, a PS InSAR or the dominant scatterer analysis has been done for mass movements at landslides in a number of places. I can't think of an example right away, but I know Haresh and colleagues had done that analysis for a landslide here in California that was moving with Sentinel-1 data. It's I don't have the reference right in front of me. What is the minimum number of connections for each interferogram to execute SBAS? Well, in this case, it's possible to run SBAS with just 1 connection per interferogram. That's why NISAR is present planning only to do the adjacent in time. So then you'll only have one connection for each, well, one ahead and one behind for each date. That's the minimum for SBAS analysis. It doesn't give you an estimate of the temporal coherence because you don't have any redundant information to estimate what the temporal coherence is. But you can do SBAS analysis with just one connection per date. For tropospheric delay with MIRIS and InSAR, yes, the MIRIS data has a coarser resolution. I think there is a way to get the MIRIS data at 300 meters. We used to have a system at JPL that would extract that. It's no longer running. It was an old technology. But you have to interpolate, and that's part of that can cause some errors. But in general, the atmosphere doesn't change very rapidly over distances of only a few hundred meters. So MIRIS corrections work really well. We also did corrections with on a satellite, a NASA satellite called MODIS. Well, it's not the satellite. The satellite was called Terra. Had an instrument called MODIS. It had a similar 1 kilometer resolution water vapor estimates. The Terra satellite is not the same satellite as NVSat or Sentinel-1. So usually the images are only usually the images were acquired about an hour different from NVSat because NVSat was in a 10 a.m. orbit and MODIS was in a 10:30 p.m. orbit, a.m. orbit, so those were close in time. Sentinel-1, they shifted the timing to 6 a.m., 6 p.m., so MODIS data was then about 4 hours different, and therefore it hasn't been effective as effective. Because of the bigger time difference nowadays between MODIS and Sentinel-1, I think people haven't been using MODIS. I worked with Zhenhong Li, who was a researcher in the UK for many years on doing MODIS corrections, and it worked quite well for NVSat because of the time difference was small, but I think it hasn't been working very as well for Sentinel-1, and NISAR will also be in a 6 a.m., 6 p.m. orbit. The main way that people do corrections nowadays is from weather models, and NISAR will be providing a tropospheric delay estimate that's derived from the European Center for Medium Range Forecasting Operational Weather Model, ECMWF. I think, in addition, the MODIS instrument is stopped operating because the Terra satellite is in the process of being deorbited. It was launched in 1999, so it's already 24 years old. Yeah, 24 years old. So it's on its last legs. The MODIS instrument is really not operational anymore. So we don't have a notebook for deriving delays from MODIS data. It was very promising 10 years ago when we had MODIS and NVSat almost at the same time, but I think people have moved away from it now.